Okay, this video is about accounting for a Morse curve, and what a Morse curve does is a Morse curve charts potential energy for atoms. So what a Morse curve will tell you how much potential energy the atoms have here when they're bonded and when I crush them together, right? That's what a Morse curve tells you. Now, a Morse curve is a graph, all right? And it's going to look like this. Potential energy is going to be dependent upon distance, all right? And Morse curves have this pretty cool shape where they kind of look like a parabola, but then they stop, and then it turns into like a weird, like a function that approaches zero, all right? And it will actually get there if the atoms are like really far apart, all right? So here's what the graph looks like. And we're going to analyze what it means in terms of the atoms. Here is when the atoms are really far apart. They've got a little bit of degree of attraction between each other, but not a lot. So they have a little bit of potential energy, it'd be negative. And then they're going to go down here, and then at the bottom, this point is when the atoms are bonded and very stable. The bond has been made, and they're just kind of chilling, all right? And up here is when the atoms are being crushed together. They're like in the musher crusher, and they're getting crushed together. All right. So that's kind of what the Morse curve is. So you can see the potential energy between the two atoms relative to their position to each other has this kind of a curve, and the atoms start far away. They get close together. They reach like an optimal distance, and then they get too close. All right. Now, so here's a good definition, all right? Here's the curve, all right? Now, the reason this curve exists and the reason it changes is because atoms always have got attractive and other repulsive forces going on. Here we have mainly attractive forces. The atoms are kind of like they're kind of like, hey, what's up? And then as they get closer, they bond, all right? Like, this is awesome. I'm getting a stable octet. These are showing you hydrogen atoms. And you've got really good, strong attractive forces. Technically, these would be coming from like the nucleus, from this guy's nucleus to this guy, that atom's nucleus, and this atom's nucleus to that. And there'd be repulsive forces between the electrons and a little bit between the nuclei. But I drew it because it would get kind of messy if I put it in the right spots. And here is when I'm really crushing the atoms together, where I've got really strong repulsive. Nuclei to nuclei, electron to electron. They don't like sharing the same space. All right. Excuse me. Please write this down. Now, here's our graph. I'm going to give you some important information about it. I'd like you to write this down. This is picometers. Here's our graph. You can see it's got that really cool shape. Now, this red area up here, when it's positive potential energy, that means the atoms are unstable, in the sense that if you let them, they're going to want to get rid of that energy over time. It's not sustainable. They don't like that energy. Doesn't mean that you can't make it happen. It just doesn't mean they won't do it, or not. They won't do it unless you make them do it. The blue is when they're stable. All right. Here's what the atoms look like in their respective spots where you're crushing, they're bonding, they're far apart. Now, this is just to explain why it's red and why it's blue. The potential energy is less than zero because the attractive forces are greater than the repulsive, and vice versa for positive. All right. Now, these graphs have some important information about the molecules themselves. and I called it the lessons from the well bottom. It kind of is thought of like a well because you have to add energy to get the atoms to separate. You have to add energy to get the atoms to separate. It has to do with where the atoms, where this dot on the bottom crosses the axis. This point on the x-axis is known as the bond length, and this axis on the bottom is known as the bond energy. Now, in this case, it would be negative, but atoms or molecules don't have negative bond energies. It would be positive. The reason it's negative is it would have to be added to the molecule to break them. All right. I hope this has been helpful and have a great day.